Okay, welcome to Engineering Mechanics Statics, Chapter 4, Equilibrium of Rigid Bodies. Okay, today we're going to talk about how for a rigid body in static equilibrium, the external forces and the moments are balanced and will impart no translational or rotational motion to the body. The necessary and sufficient conditions for the static equilibrium of a body are that the resultant force and couple from all external forces form a system equivalent to zero. In other words, the sum of the forces are equal to zero and the sum of the moments are equal to zero. Okay, and when you resolve each force and moment vector equation into its rectangular components, that leads to 6 scalar equations, which also express the conditions for static equilibrium, or sum of the forces in x equals 0, sum of the forces in y 0, sum of the forces in z, and the sum of the moments about x, y, and z are all 0. Okay, let's bring up our little pointer. Free body diagrams. We need to be able to do free body diagrams, and we've talked about that in the past, but we're going to expand on it a little bit. So the first step in the static equilibrium analysis of a rigid body is to identify all forces acting on the body with a free body diagram. So how do we do that? Well, we're going to cut away. We're going to draw kind of line through here, and this is our free body diagram. Okay, and so we want to select how much you need to have in the free body diagram and detach it from the ground, all the bodies. We want to indicate the point of application and the magnitude of all the external forces, right? So this thing has a certain amount of weight going in this direction. Has the truss itself has a certain amount of weight applied there. Now, the big thing, this is the new thing for this chapter, is we need to indicate the point of application and an assumed direction of unknown applied forces. Okay, what does that mean? Well, these usually consist of reactions on the ground or other bodies which oppose the possible motion of the rigid body. So what does that mean? Look at this pin right here. Okay, we have this thing. Right now, this pin can do two things. It can resist it from going up or down, and it keeps it from going this way and this way. Now you look here, this is what's called a rocker. This thing is not going to prevent it from going up and down, but it'll definitely keep it from going into the wall. And so there's a reactionary force there in the wall. And so we go through, and things that you cut through, you can cut through anything you want. That's the nature of free body diagrams. You can go through and you can cut through anything you want. But when you cut through something, you need to replace it with the appropriate unknown force. And that's, so in this case, since we cut through a pin, you replace it with 2 unknowns. And here we cut through a rocker, and so we replace it with 1 unknowns. And you need to make sure you include the dimensions necessary to compute the moments of the forces. Okay, let's take a second to talk about these reactions at supports and other types of connections for a 2D structure. Okay, so when we're doing free body diagrams, again looking here, we have this free body diagram, right? And you have to cut through some things. And you have to replace these things, if you will, that you're cutting through with unknown forces. Well, these things are different types of supports and connections. And different types have different number of unknowns. So here, let's look at these cases. These are all cases where they have one unknown. That unknown is the actual magnitude. You know the direction. You know that this is going to push up. You know that this is going to push up. You know that this is going to be in this line of action, right? So you know the direction of a roller or a rocker. You just don't know the magnitude. Well, another one with just one unknown is a short cable. So, cables are just going to be in the direction of the cable, right? So it's going to be some tension, or a short link, which you can have tension or compression. And so in that case, you know the direction, you know it's in that direction, but you just don't necessarily know the magnitude. And the last example is a collar on a frictionless rod or a frictionless pin in a slot, same deal. It's going to be perpendicular to that member right here. Now, but there's also ones, connection supports that have more than one unknown. So consider a pin. We had, going back here, we had this was a pin, right? So what does that pin do? It keeps it from falling up or down, and it also keeps it from going left or right. So it has 2 unknowns. So you have a pin. You also have a rough surface. So it just means it sticks to the surface. So it won't slide this way. It won't slide in the x direction or y direction. Or sorry, it won't slide this way, and it also won't go in this direction. It'll resist force in that direction. So you can express these as either 2 forces, an x and a y force, or you can express them as a force and an angle. Then lastly, you have the 3 unknowns, and that is, say, a fixed support. You put this thing into concrete. Now what's going to happen? You can't pull it up, you can't push it down, you can't push it left, you can't push it right, right? So you have the x and y planes, or x and y axes. It resists force in those. But this one is unique. It also resists moments. If you try to twist it over, it wouldn't let it twist. Whereas here, a pin, you can rotate it as much as you want. This fixed support, it won't let it twist. So when you go in to put it in its axis, you have the or as unknowns. You have an x direction force, you have a y direction force, but you also have a moment or a couple, and that's the three unknowns. Okay, so what direction do you put it in? Well, bottom line is if you know the direction of the force, put it in. Otherwise, just make it up. Just pull it out of the air, make it up. What's going to happen, your final answer will tell you if you were right or not. If your final answer is positive, that means that you drew it in the right direction. If it's negative, it just means that you drew it in the backward direction. Either way, if you draw the arrow to the right and you get an answer of -5, you know that you have 5 units to the left. It's just that easy. So the thing is once you draw those arrows, be consistent. Stick with them until you're done with the problem. And if you get negative numbers, that's fine. Just make sure you keep track of the positives and negatives and you account for them in the end. Okay, now equilibrium of a rigid body in 2 dimensions. Okay, so we have for all forces and moments acting on a 2-dimensional structure, what do we have? Well, it's 2-dimensional, so our forces in z are 0, right? That's 2 dimensions. And our moment in x and y is also 0, because that's the moments. You have to have a force in the z direction to get a moment in x and y. And so therefore we're going to claim our moment in z is just our moment. Okay, so given that, our equations of equilibrium simply become the sum of the forces in x equals 0, the sum of the forces in y equals 0, and now the new one for this chapter is the sum of the moments equals 0. So we've been doing this since chapter 2 and 3, it's sum of the forces in x and y. Now we're going to introduce the idea that the moments also have to be 0. And this is for the moment, it can be about any point A on the plane of the structure, so it can be anywhere. Okay, so these 3 equations can be used to solve no more than 3 unknowns. Okay, now here I'm going to say something a little bit strange. The 3 equations cannot be augmented with additional equations, but they can be replaced. Okay, that sounds really weird, but here, what am I saying? Well, generally speaking, we have here some of the forces in x, some of the forces y, and some of the moments. Well, you could go through and you could do a problem like this. So you look at this problem. You have 2 forces, 2 unknowns here, and 1 unknown here. I could take the sum of the moments at this point. If I take the sum of the moments at this point, I'm assuming P, Q, and S are all known. So B is going to pass through that point, so it's going to have no moment. AX is going to pass through that point, so it's also going to have no moment. So you can use that equation to solve for AY. And then you're going to say, you know what, I'm going to take the sum of the moments about A. Okay, so now I'm going to AX and AY are going to pass through that point, but now B does not, and so then I can solve that for B. So I've now used the sum of the moments at 2 different places, so I've used the moments equation twice, just in different spots to determine 2 different variables. So you think, hey, I can just keep on going. What if I take the moment about this point right here? Well, hey, I can take the moment about this point. I already know this one, so I'll plug in that. I already know this one, I can plug in that, and then I can solve for this last one right here. The thing that is going to be tempting is you're going to think that magic can happen, and all of a sudden if you take the moments enough places, you can start solving for 4 or 5 or more equations or unknowns. You can't. When you do, if you substitute, say, a sum of the forces for a sum of the moments, that's fine, and then sometimes it's easier. But be aware that when all is said and done, 3 equations and 3 unknowns. You're not going to magically come up with a way to solve for 4 equations. It just can't be done. And so even though you might not ever take the sum of the forces in x, you are, by taking the moments at different locations, you are effectively doing that. Okay, we have a concept called statically indeterminate reactions. Okay, so here's the deal. We have this frame truss thingy, and we have a couple forces on here. You'll notice this is a pin and this is a pin. So we're going to draw the free body diagram of that. Okay, so here this has the x and the y, sorry, the x and the y component of P, the x and the y component of Q, the x and the y component of X, and then you have the weight. But here we drew our free body diagram where we cut through here. So since we cut through a pin, we replace it with 2 unknowns, x and y, and then we come through here and we draw our free body diagram through there. So we cut through another x and y. Now, how many equations do we have? It's a 2-dimensional thing, so we only have 3 equations, and so how many unknowns can we solve for? 3. But we have 1, 2, 3, 4. This is what's considered, it's more unknowns than equations, and this is considered statically indeterminate. Okay, now the flip side of that. Now we have these same forces, but we have 2 rollers. Okay, so you have all these same things, but now you just have forces here and here. Well, how many equations do we have? We have 3 equations, but how many unknowns? We have A and B. We only have 2 unknowns. This is fewer unknowns than equations. It's called partially constrained. And what's going to happen? This thing's going to move, right? It's not going to be a static object. It's going to accelerate. So then we're going to come here. Hey, 3 rollers. So we have 1, 2, 3 unknowns. So we have 3 equations and 3 unknowns. So we're good to go, right? No, it's still possible, even when you have the right number of equations and right unknowns, for it to be what's called improperly constrained. It turns out when you go and look at this, you're not going to be able to, there's not going to be no force that's going to resist it in the x direction, and you're not going to be able to differentiate how much of the vertical is in which one of these things. So just because you have the right number of equations and unknowns doesn't necessarily mean that you're going to be able to solve the problem. Now, for the most part, we can solve most of these problems, but be aware that it is possible to have what's considered a statically indeterminate reaction. Okay, let's do some examples. We got a few examples from the book.